Welcome to episode 2 of the Quantum Rings Quantum Summer School. Last week, we covered the mathematical prerequisites for the course, including some linear algebra, complex numbers, and quantum mechanics notation. Today, we're going to be focusing on single qubits, more specifically how we manipulate our qubit states with gates, and how measuring our qubit works. In this course, we will build up to working with multi-qubit circuits to perform complex quantum algorithms. We can, however, perform a really cool protocol with just a single qubit. We will discuss a quantum key distribution protocol, which is a quantum solution to the key distribution problem in cryptography. Quantum key distribution leverages the quantum superposition of the qubit in order to protect the key from eavesdroppers, and we're going to see how this works later today. But first, we need to understand quantum gates and quantum measurement, so let's get into it. Today, we're going to be talking about single qubits. We'll start off by talking about measurement, then we're going to talk about single-qubit gates, and finally we'll talk about a use case where you can take advantage of a single qubit, which is quantum key distribution. Last week we talked about math prerequisites and quantum mechanics notation for the course, so if you need to catch up, feel free to look back at that previous video. First, I want to talk about the difference between a classical and a quantum bit. So a classical bit is the bits in your laptop or your iPhone. The only possible states that it can be in is 0 or 1. And you can consider measuring the state of your classical bit would just be looking at your bit and checking what state is it in. And before you measure your classical bit, it's already going to be in the state that you measure it to be in. So if you measure 0, then it was already in the 0 state before you started measuring. And if you measure 1, it was already in the 1 state before you started measuring. So in this sense, for a classical bit, measurement is deterministic. For a qubit, on the other hand, the possible measurement outcomes are the same. We can only measure 0 or 1. But before we measure our qubit, it is in some superposition state of 0 and 1. And when we measure our qubit, it collapses to either the 0 state or the 1 state. And there's some probability that you'll measure 0 and probability that you'll measure 1, but you don't know what it's going to be before you measure your qubit. So for a qubit, measurement is probabilistic. And then I just want to note that after you measure your qubit, it remains in that state. So if your qubit is in some superposition state, you measure your qubit and you measure 0, and then you leave your qubit alone, come back a while later, you've done nothing to it, it will still be in the 0 state. And each time you measure it, it will keep remaining in that state until you manipulate it with some gates. So last week we talked a little bit about what an arbitrary quantum state looks like. So we can express it as superposition of 0 and 1, so just a linear combination of the 0 state and the 1 state. And alpha and beta are the amplitudes of the 0 and 1 state, and they can in general be complex numbers. And then Born's rule tells us the probability of measuring 0 and 1 given this arbitrary quantum state. And the probability of measuring 0 is going to be the amplitude of the 0 state squared. And here I mean alpha times its complex conjugate. And then the probability of measuring 1 is going to be beta squared. And this provides us with a normalization condition for our quantum state. We know that we have to measure something, and the only two measurement possibilities are 0 and 1. So it better be the case that the probability of measuring 0 and the probability of measuring 1, which are disjoint, should be 1. So that tells us that the magnitude of alpha squared plus the magnitude of beta squared ought to be equal to 1. So now what we have actually is 4 degrees of freedom, because alpha and beta are both complex numbers. So there's a real part and an imaginary part for each one. But we have a normalization condition, and we can also choose that alpha is real, because otherwise there's some global complex phase that we can pull out front that we don't care about. So we can pick alpha to be real, and then there's the normalization constraint, and that leaves us with 2 degrees of freedom. 2 degrees of freedom can put us on the surface of a sphere of radius 1. And we call this the Bloch sphere. So now we can express our quantum state not in terms of alpha or beta, but in terms of theta and phi. So generally speaking, this would be cosine theta over 2 is 0, plus e to the I phi sine theta over 2, 1. And what that looks like is we'll have the 0 state at the North Pole and the 1 state at the South Pole. And then we can have our arbitrary quantum state pointing to somewhere on the surface of the sphere. And then theta is the polar angle down from the z-axis. And we can project our quantum state down to the xy plane. And then phi is the azimuthal angle from the x-axis. So we can think about what some of our common states look like on this Bloch sphere. So first we have our states 0 and 1, and we already know that these lie along the z-axis. And the 0 state is when theta equals 0, and phi can be anything. And then the 1 state is when theta equals pi, and phi equals 0. And we can look at some other common states as well. So one that we might be interested in is the states that lie along the x-axis. And we call these the plus and minus states. You can double check this for yourself, but these states look like 1 over root 2, 1 over root 2, and 1 over root 2 minus 1 over root 2. And both of these have theta equal pi over 2. They lie on the equator, but one has phi equals 0 and the other has phi equals pi. We can also consider the states that lie along the y-axis. That would be these ones here. And we call these plus I and minus I. And again, we can express these pretty straightforwardly. So this one will be 1 over root 2, I over root 2. And then this one would be 1 over root 2 minus I over root 2. And both of these, again, have theta equals pi over 2 because they lie on the equator. But then one has phi equals pi over 2, and the other has phi equals minus pi over 2. So one thing that we could ask is, what do the states plus and minus I have in common? Well, for all of them, the amplitude of the first coefficient squared is 1/2, and the amplitude of the second coefficient squared is 1/2. And this is the probability of measuring 0, and this is the probability of measuring 1. So all 4 of those states are equal superpositions of 0 and 1. More generally speaking, any state that lies on the equator of the Bloch sphere is going to be a 50-50 chance of measuring 0 or 1. And then if you lie somewhere in the upper hemisphere, you'll be more likely to measure 0. And if you lie somewhere in the lower hemisphere, you'll be more likely to measure 1. So now we understand a bit about how to represent our qubit states mathematically and how to visualize them on the Bloch sphere. Now we need to talk about how we manipulate our quantum states. In order to do complex quantum algorithms, we need to be able to manipulate our qubits in order to do something useful. And we do that with gates. A gate is just an operator which maps one qubit state to another. And what is a requirement for a gate, which, remember, in linear algebra terms is just a matrix? We need it to be unitary. And what does that mean? It just means that the Hermitian conjugate of the matrix is its own inverse. So in other words, if you have some matrix U, then U dagger U is equal to U dagger, and that's equal to the identity. And there's kind of 2 reasons for that. One is that it preserves the norm of a quantum state. So if you using a gate to map us from one qubit state to another, it better preserves the normalization condition. And 2, we need all of our quantum gates to be reversible. And so U dagger is just the reverse of U. And so if you apply U and then U dagger and you go back to where you started, then that's good. That means it's reversible. Generally speaking, because we can visualize our qubit states on the surface of a sphere, and any gate just maps us from one point on the sphere to another, then we can think of every single qubit gate as being a rotation. So now let's look at some of our common gates. The first gate I want to talk about is the X gate, which has this form, 0, 1, 1, 0. And we can think about the action of the X gate on our basis states 0 and 1. So first, we can think about the action on the 0 state. This would give us 0, 1, which is the 1 state. And then we can also consider the action on the 1 state, which will flip us to the 0 state. And so we call the X gate the bit flip gate, because it flips 0 to 1 and 1 to 0. If we look at this on the Bloch sphere, the action of the X gate is to do a 180-degree rotation around the x-axis. So if we start in the 0 state and apply the X gate, we will rotate around and end at the 1 state. Another example is that if we start at some arbitrary state, for instance here, we would rotate around 180 degrees and end up over here. Another gate is the Z gate, and this is 1, 0, 0, minus 1. And we can think about the action of the Z gate on our basis states. We can write out the matrix multiplication, but just cutting to the chase. When we act on the 0 state, we get back the 0 state. And when we act on the 1 state, we pick up a minus sign on the 1 state. And this is a phase, which is actually just e to the I pi. And that's why we call the Z gate the phase flip gate. We can think about 2 examples of the Z gate acting on a state. Again, it's just going to be like the X gate, a 180-degree rotation around the Z axis. So if we act with the Z gate on the 0 state, nothing will happen. It will just stay where it is because it's just rotating around its own axis. But for instance, if we started in the plus state, then we would have a 180-degree rotation around and end at the minus state. And this makes sense too because the plus state is 1 over root 2, 0 plus 1 over root 2, 1. And the minus state is 1 over root 2, 0 minus 1 over root 2, 1. So we picked up a minus sign on the 1 state. The Y gate is very similar to the X and Z gate. It, again, just does a 180-degree rotation around the y-axis. So here it would map the 0 state to minus I times 1, and the 1 state to I times 0. And again, it's going to be a 180-degree rotation around the y-axis. So it would rotate the 0 state from here down to the 1 state. Another really important gate is the Hadamard gate, which looks like this. The Hadamard gate maps the 0 state to 1 over root 2, 0 plus 1 over root 2, 1, which we remember is the plus state. And it maps the 1 state to 1 over root 2, 0 minus 1 over root 2, 1, which is our minus state. So the 2 main cases where we care about this is the 0 and the 1 state. And the action of the Hadamard gate is to rotate us around the axis that lies at a 45-degree angle in the xz plane, and is also a 180-degree rotation. So it will rotate the 0 state down to the x-axis to the plus state. And we'll rotate the 1 state up to the x-axis to the minus state. The Hadamard gate is how we create equal superposition states really easily. The last two gates I want to talk about are the S gate and the T gate. The S gate, which looks like this, is a 1/4 rotation around the z-axis, so 90 degrees. So for instance, if we start in the plus state, we will rotate 90 degrees and end up in the plus I state. And then the T gate is a 1/8 rotation around the z-axis. So if we start in the plus state, we're to rotate 45 degrees and end up here. Now that we've covered these 6 foundational gates, let's move over to the coding notebook and put this into practice. So now you can pull up your coding notebook in QBraid. If you need to still set up QBraid or your Quantum Rings account or anything like that, check back in the last video where I went over that. If you don't see episode 2 here, what you'll need to go is click on this part here which says Git, and then go up to the top where there's these cloud symbols, and then you're gonna click on this one which says Pull Latest Changes, and then you should be able to get the newest notebook. For each time that a new notebook is released, you'll have to repeat this step. Another important thing that you want to do is you want to make sure that you select the right kernel for the notebook, which should be Python 3 Quantum Rings. And if you don't have that, make sure you install the Quantum Rings environment. Again, check back last week on how to do that. So the first thing that we'll want to do is run this first cell to import all the libraries we need and also load our Quantum Rings account. And then these are some helper functions that we'll use later. So first we want to talk about single-qubit gates. So we learned about these 6 foundational gates, X, Y, Z, which are 180-degree rotations about their respective axes, the Hadamard gate, which creates an equal superposition of 0 and 1, starting from the 0 or the 1 state. The S and T gates are 90-degree and 45-degree rotations around the z-axis. Generally speaking, every single qubit gate is a rotation. Throughout the notebook, there are these quiz questions. So if you see a cell that says display quiz, just run that cell, and there will be these quiz questions shown here. You can try yourself and click on answers, and we'll tell you if it's correct or not. And this is a good way to check your understanding of the material that we've covered so far. So we can use the Qiskit toolkit to very easily apply gates and then visualize the action of those gates. So if we use the function run and plot, we can show the final state of a quantum circuit. And by default, our qubit always starts in the 0 state. So first we can do a quick demo of the X gate. And one thing I want to point out is that some of the circuits in the notebooks have names, and these names will show up in your Quantum Rings execution history. So this will be our way of checking if you're actively participating in the course to see if you're running the cells in the coding notebook. So for the X gate, we can have a quantum circuit with 1 qubit and 1 classical bit. And then we can apply an X gate, and then we can measure qubit 0 to the 0th bit in the classical register. And we already know that this is going to flip our 0 state to our 1 state. We can also show a Y gate. By applying a Y gate on the 0th qubit. And this will also flip our state from 0 to 1, but it will do it in a different way. Instead of rotating around the x-axis, we'll rotate around the y-axis. With the Z gate, same thing. Now nothing has happened. But this makes sense because the Z gate is a 180-degree rotation around the z-axis. so it won't do anything to the 0 state. We can also prepare an equal superposition by using the Hadamard gate. This rotates the 0 state down to the x-axis. So if we want to see what the action of the z-gate does, then we can prepare the plus state and then apply the z-gate. And then we should be able to see a 180-degree rotation around the z-axis to the minus state, the minus x-axis. So here you can try and test that out with the z-gate, and you can also try testing out the s and t gates, which are phase shifts. So first prepare the plus state, and then see the s and t gates acting on those. There are more quiz questions here as well. We can also make animations of our gates to better understand what's going on. So in practice, we don't instantaneously apply a quantum gate. We apply a rotation, and we call this unitary evolution because our qubit state is evolving under a unitary operator. And so here we can define an arbitrary rotation axis, rotation angle, and initial state. So here, for example, we can recreate the x gate, but we want to start from the state plus I. So our axis of rotation is going to be the x-axis. Our rotation angle for an x gate is 180 degrees. And our initial state is going to be 1 over square root 2 and I over square root 2. So here we get our animation. We have our rotation axis is the x-axis. We're starting in the plus I state. And then we have a 180-degree rotation around the x-axis. So feel free to play around with this yourself and try out whatever axis, rotation, angle, initial state you want to try out. So now let's explore the nature of quantum measurement. So we know that our qubit exists in a superposition state prior to measurement, but the only possible measurement results are 0 and 1. So we need to think a bit carefully about what we can learn from measuring a qubit. So first, let's load our backend, which we'll use throughout this section. And now we want to compare the plus state and the minus state. So first, let's make a circuit which prepares the plus state, and then we want to measure the qubit 1,000 times. So we can do this by adding a Hadamard gate on our qubit and then measuring, and we're going to do 1,000 shots, and we can see our distribution of counts. So we measured 0 501 times and 1 499 times. And we can do the same thing by preparing the minus state. So first we should flip our bit to the 1 state and then apply the Hadamard gate to get to the minus state. So first we'll do an X gate to flip our bit, and then a Hadamard gate to bring us to the minus state. And here we get 495 counts of 0 and 505 counts of 1. So the question is, can we tell the plus and minus states apart based on these measurements? So the answer is no, we can't really tell them apart. But what information did we learn? We learned that these are roughly equal superposition states. We don't know exactly that they're on the equator because measurement is probabilistic, but we know that we roughly measured 50-50 of 0 and 1, so our qubit state lies somewhere on the equator. But we didn't learn anything about the phase of the state. So what can we do before measurement to be able to distinguish with 100% certainty between the plus and the minus states? What we can do is we can rotate into the x basis. So we know that the Hadamard gate maps 0 to plus and 1 to minus, but it also maps plus to 0 and minus to 1. So if we apply a Hadamard gate right before measurement, then we will align the plus state with the 0 state and the minus state with the 1 state, and we'll be able to distinguish them. So here we're preparing the plus state, but then performing a Hadamard before measurement, and we always measure the 0 state. And then if we rotate into the x basis, here with the minus state, we will always measure 1. So a challenge for you is to see if you can come up with a protocol for measurement that can distinguish with 100% certainty between the plus I and minus I states, and then test it out to make sure it works. Throughout the rest of the course, we're going to be using more than 1 qubit, but for now, let's talk about something useful you can do with just 1 qubit, and that's quantum key distribution. We're going to talk about the BB84 protocol, which is named after Bennett and Brassard, who came up with the protocol in 1984. The general premise is this. You have 2 parties, Alice and Bob. Alice has some information that she'd like to send to Bob, so she's going to want to encrypt it, send it over to Bob, and then Bob is going to decrypt it. And the way they're going to do this is by having some shared key between them. But what happens if there's some other person, who we'll call Eve, who somehow has their shared key? Somehow she knows it. Then if she intercepts the information, then she can just use the key to decrypt the data, and then she'll have stolen the information. So the question is, how can we create a shared key such that we can be certain that nobody else knows it? And this is quantum key distribution. So for QKD, we use the laws of quantum mechanics to securely create a shared key. And not only that, we'll be able to detect if anyone tries to eavesdrop and learn the key. So in order to do this, Alice and Bob are going to share 2 things. One is a quantum channel, and one is a classical channel. In the quantum channel, they can send quantum bits, and in the classical channel, they can communicate normally, like over text or something. And then Alice is going to have a qubit, and the first thing she's going to do is choose a bit. So that's either going to be 0 or 1. And then she's going to choose a basis. And the 2 bases she has to work with is either Z or X, and she can make this choice for either of these cases. So if she chooses 0 and Z, then she's going to prepare the state 0. And if she chooses 0 and X, then she's going to prepare the state plus. Similarly, if she chooses the state 1 and Z, she'll prepare the state 1. And if she chooses X, she'll prepare the state minus. And then she's going to send this over to Bob, and Bob has a choice. So Bob is going to choose a basis. And he can either choose the Z basis, in which case he just measures the qubit, or he can choose the X basis, like we saw in the coding notebook, where he can apply a Hadamard gate and then measure the qubit. So let's consider the different scenarios that are possible. So the first is if Alice and Bob choose the same basis. Then what we have is Alice prepares her bit over here. This could either be a 0 or a 1. And then if Alice and Bob both choose the Z basis, so that's what's happening here, then neither of them are going to apply a Hadamard gate. But if they both choose the X basis, then they're both going to apply a Hadamard gate, because Alice needs to apply a Hadamard to prepare either the plus or the minus state, and then Bob needs to apply a Hadamard before measurement. But we know that the Hadamard gate squared is the identity. So really, having 2 Hadamards in a row is like doing nothing at all. So in these cases, whatever Bob is doing is exactly undoing what Alice has done. And so that means whatever Bob measures has to be what Alice has sent. Now consider the case that Alice and Bob chose different bases. So either Alice chose Z and Bob chose X, or Alice chose X and Bob chose Z. We can consider 2 cases here. In both cases, there's only 1 Hadamard before Bob measures, so we can condense it down like this. If Alice's bit was 0, then at this point in the circuit, the qubit is in the plus state. And then when Bob measures, he'll measure 0 with 50% chance and 1 with 50% chance. If Alice chooses the bit 1, then at this point in the circuit we'll be in the minus state, and Bob will have a 50% chance of measuring 0 and a 50% chance of measuring 1. So in this case where they choose different bases, basically Bob's result has nothing to do with what Alice sent. So they only are going to agree when they chose the same basis. This brings us to the full protocol. So the first step is Alice is going to pick n bits, so a string of zeros and ones. Then Alice and Bob are going to pick bases for each of the n bits. Then Alice is going to prepare each bit in the chosen basis. So if that's z, 0 and 1, if that's x, plus and minus. And then Bob is going to measure each bit in whatever basis he has chosen. And then finally, they're going to announce publicly over the classical channel their bases. And this is totally fine to do because they're not announcing any part of the key. They're just announcing what bases they chose to perform measurements, which gives you no insight into what the key is. So then, if they chose the same basis, they're going to keep the bit because they should be in agreement. And then if they're in a different basis, they're going to discard that bit. Now, if everything is perfect, then every single one of the bits where they measured in the same basis should be identical. But there could have been someone interfering along the way. And so what they need to do is they need to compare a portion of the remaining bits in their key. And if all of those are in agreement, then they can conclude that it was safe, no one was eavesdropping, and they can use this as their shared key. Of course, the bits that they compared publicly, they should no longer use in their shared key, but whatever is remaining they can use. But if there's any discrepancies at all between the bits that they compare, then they know that they've been compromised. So they know that someone was tampering with the qubit somewhere along the way, and they discard all their bits and try again another time. So in actuality, Alice and Bob don't know what happens in the region between them. So once Alice has sent the bit, and before Bob has received it, it's like a black box. And so if anything happens in that black box that alters the state of the qubit, then whatever Bob does will not exactly undo what Alice has done. So even if Alice and Bob are working in the same basis, Bob's measured bit may not agree with what Alice has sent, and that's how they're able to detect an eavesdropper. So one question you might ask is, why can't Eve just copy the qubit? So Alice is sending a qubit over to Bob, and then why can't Eve just grab the qubit, make a copy for herself, and then wait until Alice and Bob announce what bases they chose. And then she knows that whenever they were in agreement, she should also measure in that basis. And then she just performs her measurement and she learns their key in that way. This would be a pretty clever technique, but unfortunately, Eve is out of luck because there's a thing called the no cloning theorem, which says that there is no quantum operation which can clone an arbitrary quantum state. So we can quickly prove this. We can suppose that such an operation exists. So you have some operation U applied to some state psi and the 0 state, and then after you apply it, we just get 2 copies of the state psi. And so if we re-express psi as our arbitrary wave function alpha 0 plus beta 1, then we can write this as psi, because it just makes a copy. And then we can just FOIL this out. And we'll find alpha squared 0, 0 plus alpha beta 0, 1 plus alpha beta 1, 0 plus beta squared 1, 1. But we also know that any operators, any matrices, must act linearly. So what that tells us is that U acting on alpha 0, 0 plus beta 1, 0, it must distribute into that. So then we'll have alpha U0, 0 plus beta U1, 0, and this is clearly because U just performs a copy, alpha 0, 0 plus beta 1, 1. But we said that alpha and beta were arbitrary, and these two expressions are clearly very different. So there is no such operation that can clone a quantum state. Now that we've had a chance to explore the concept and math behind this, let's move over to the coding notebook and try it out. Now let's come back to the coding notebook. So here we're going to build up the BB84 protocol. So just to recall, we have Alice. She's going to prepare a qubit in a chosen basis, send it over to Bob. He's going to measure in a chosen basis, and then they're going to compare if their bases agree. If it does, they're going to keep the bit. If not, then they're going to discard the bit. So let's take a look at this in action. So let's say we have 5 bits. Alice is going to randomly choose 0 or 1, and then Alice and Bob are both randomly going to choose bases. So 0 would be the Z basis and 1 would be the X basis. And then for each of the bits, we're going to make a quantum circuit with 1 qubit. And then if Alice chose the bit 1, then she needs to apply an X gate to flip the state of our qubit. If Alice's basis is the X basis, then she needs to apply a Hadamard gate to rotate into the X basis. And then finally for Bob, if his basis is the X basis, then he also needs to apply a Hadamard gate to rotate the X basis back into the Z basis. So now we can see what this looks like. So here for the first one, we see that Alice prepared the bit 0, she chose the basis Z, and Bob chose the basis X, and then Bob measured 1. So they picked different bases, and Bob measured something different than Alice, which he had a 50% chance of doing. Here, Alice and Bob chose the same basis, and Bob measured exactly what Alice prepared. Here, they chose different bases, and their answers differ. You can run this a bunch of times and see how it works with a different combination of Alice's choices of bits and basis and Bob's choice of basis, and just get a sense for how it works. Down here, there's a full protocol where you can run for many more bits. So for instance, with 20 bits, you can see that Alice has some bit string that she builds up, Bob has some bit string that they build up, and they have their choice of bases. Then they're going to go through and post-select. So they're going to announce over their public channel which bases they used, and they're only going to keep bits where their bases agreed. And so in the end, Alice and Bob are going to have identical keys. An important thing to note here is that these bits have never been announced publicly. These have only been kept private between Alice and Bob, so it's 100% secure and no one else could possibly know the key. Now we want to consider adding in Eve. So Eve is our eavesdropper. There's different things she can try to learn Alice and Bob's key. So one potential attack is a simple measurement attack, where as the qubit is coming, she just intercepts it, measures it, and sends it along to Bob. And so in this part of the notebook, you can try out adding in Eve's simple measurement attack, and you can see how that impacts Alice and Bob's shared key, and if they're able to detect her or not. And then if you want an extra challenge after that, you can also try the mimicry attack, where Eve mimics Bob and tries to disguise herself by also randomly choosing bases. That's a wrap on episode 2. Today we learned about the nature of quantum measurement, single-qubit gates, and a quantum key distribution protocol called BB84. Next week we're going to step it up and move to 2 qubits and more, and we're going to be talking mostly about entanglement, where 2 qubit states are inextricably linked. Thank you so much, and see you next week.